So before we get to titrations, we want to finish out section 3 and talk about the things that impact solubility. And when it comes to solubility, there are 3 primary factors that will impact how soluble or insoluble a substance is. We've already talked a good bit about the first one, structure. Whether a molecule is polar or non-polar says a lot about whether or not it's going to dissolve in water or if it's going to dissolve in an organic kind of material. That's where we apply that like dissolves like principle. The other 2 factors that we want to look into are temperature, and based on our own personal experiences, we should have at least a general idea of what that trend looks like. We know that when temperature goes up, solubility tends to increase as well. Anyone that's ever made sweet tea will tell you that one. It's a lot easier to add the sugar when the tea is brewing than when it's been iced. Cold water dissolves sugar a lot less easily than hot water does. And then we're going to want to look at pressure effects as well. And in particular, this affects gas phase solutes only. So when we have a gas dissolved in a liquid, we're going to look at pressure effects of that particular phenomenon. So as far as temperature is concerned, we know that for the most part, most solids are going to be more soluble in water as temperature increases. We know that from our own experience. We can pack a heck of a lot more sugar into hot water than we can into cold water. One interesting little side note that's going to go along with this temperature impact actually has the opposite trend for gases. Gases tend to be more soluble in cold water than warm water, and that has to do with the energy of the molecules. When we increase the energy of the molecules, it's much easier for those gases to escape because there is more energy overall in the system, and the gas will find its way out of the solution a lot more easily since the molecules inside of the solution are moving faster. For pressure, though, it's interesting. Pressure really has no impact whatsoever on the solubility for solids or for liquids. If I increase the pressure of my reaction vessel to 4,000 psi, it's really not going to change how much salt I can dissolve in water. It's not going to really impact how much alcohol I can dissolve in my water either. But for solubility of gases, pressure has an enormous effect. In fact, we can say definitively that the solubility of a gas in water is directly related to the pressure above the water. And we call this relationship Henry's law. So this is another kind of gas law. It's a different kind of gas law, though. We're not talking about the relationship between temperature and pressure or volume and temperature for a given gas sample. What we're talking about is how much liquid, or excuse me, how much gas can we dissolve in a given amount of liquid, varying by the amount of pressure that exists right over top of that liquid. So just as a graphical kind of point of comparison, you can see in this graph that for solids, for the most part, we see a positive trend in an upward direction for temperature and solubility. For everything other than the cerium-3 sulfate here, we see that as the temperature increases, the solubility increases. And in some cases, it increases by quite a bit really fast. Look at those curves for the calcium chloride and the potassium nitrate. Very, very steep slopes on those curves. But for gases, we see the opposite trend. Gas solubility tends to decrease quite considerably as the temperature increases. And we already kind of went over the reason why. At those higher temperatures, the solute particles and the solvent particles all have more kinetic energy. Since we're talking about a gas, and a gas already has a high amount of kinetic energy, what's holding it in the liquid is basically the liquid is trapping it. And if the liquid's moving around a lot more, it's not as good at trapping that gas on the inside. Impact of this particular thing? Well, dissolved oxygen. One of the key attributes for aquatic life, for rivers and streams, lakes and oceans, is the ability of oxygen to dissolve in that liquid. When oxygen is plentiful, we will find that lots of wildlife is going to be able to live there, or at least it's going to be capable of living there. Where oxygen is deficient, that's where we tend to see things happen. Things like large amounts of fish dying. In swamps, things like eutrophication, where eventually that pond, because it doesn't have a freshwater supply to feed it, eventually gets smaller and smaller and smaller and smaller as the plant life around it basically sucks up the resources and turns it into a marsh. From an environmental standpoint, a lot of different industrial zones will use river water as a cooling agent for their machinery. And they'll pump in the cold water from the river, cool their machines with it, and then dump the warm water back into the river. This is a form of what is called thermal pollution. And that thermal pollution usually is detrimental to wildlife right around that industrial zone. Because the warmer water leads to lower dissolved oxygen counts. And if there's lower dissolved oxygen counts, then there's just not enough oxygen there to sustain significant portions of life. The fish either die or they move on to somewhere else where it's not as dangerous for them. We can quantify this relationship using something called Henry's Law. Now, what Henry's Law tells us is that the concentration of a relatively insoluble gas, and most gases are relatively insoluble in water. So when we say sparingly soluble, what we mean is, for the most part, it's not soluble. Only small amounts of that gas actually dissolve. But the amount that does dissolve is directly proportional to the partial pressure of the gas that it exists in. Well, I want you to think about the best analogy that I can give you comes from this. A bottle of soda that has been unopened. Now, when this bottle is unopened, we have high pressure in that airspace right above the liquid. And we know that we have high pressure in that space because what is the first thing that we notice when we open up that cap to that brand new bottle of soda? Two things happen immediately. Okay, the first thing that makes that hissing sound. Why does it make that hissing sound? That high pressure soda, that high pressure gas that was used to bottle it now escapes. So that's what that hissing sound is. That's the high pressure gas, the high pressure carbon dioxide that is pumped into the bottle right before it is sealed. It escapes. What's the other thing that happens immediately when you open a bottle of soda? The bubbles. We start to see large quantities of bubbles inside of the bottle. Why is that? Because we have released that pressure, the carbon dioxide that was forced into that solution now is going to start to escape. Because the pressure has been released, Henry's law tells us that since the pressure above is now lower, the carbon dioxide that was once dissolved in there is now going to come out of the solution. It's going to immediately start to effervesce. It's going to immediately start to bubble because the pressure inside, which was once high, is now considerably lower. And that kind of trend is going to continue the longer that that bottle is left open. Because as that bottle is left open, we're going to see more gas escaping as the pressures start to hit an equilibrium with atmospheric pressure. And also, as this warms up, the other factor of gas solubility comes in as well. You leave a bottle of soda sitting out on the counter for a while, it starts to go flat on you. Why does it start to go flat? Temperature is rising, temperature is increasing. Carbon dioxide is less soluble in the warm soda than it was in the cold soda. So, any questions about Henry's law? That's kind of the big idea in a nutshell here. So, when we think about Henry's law, that's what I want you to think of. I want you to think about a bottle of soda. When is a bottle of soda at its fizziest? It's got to be cold, and it's got to be as close to the fresh, as open as possible. It's going to be the fizziest when you pull it right out of the fridge, open it up for the very first time. That's when it's at its fizziest, because all of those conditions that allow that carbon dioxide to be in the liquid are going to be at their maximum. You're going to have the highest pressure above the solution, and you're going to have the lowest temperature of the solution itself. We're going to get more gas dissolved in that point than anywhere else. Now, if you're in the business of liking flat soda, best thing that you can do, open that thing up, pour it into a big container, and let it warm up. You'll get rid of that gas quick. All right, so if you recall, we did the majority of this material here from 11.4 last Friday. So we're going to move now into talking about how we use those concentration values to solve problems and to do some quantitative kinds of analysis. in particular, what we're talking about here is a titration. So a titration, this is an analytical technique, a process where we use the concentration of one solution where we know its concentration very, very well to figure out the concentration of another solution that we do not know well. And we do this via chemical reaction. Now, there are lots of different titrations that exist. Technically speaking, any reaction between two solutions can be solved using a titration and a titration equation if we are interested in looking at the concentration comparison of one of the reactants versus the other. Now, if we're trying to figure out how much product we made, a titration is not going to help us really with that. There are other kinds of calculations that we would have to do. But if I'm trying to figure out the concentration of a solution by using another solution to do it, a titration is the primary means of doing that. Now, the most common types of titrations are acid-base titrations, where I've got an acid and I've got a base, and I'm using them to try to figure out one's concentration against the other. When it comes to titrations, there are two terms that are thrown about. I want to point them out to you because they are often very easily confused and often described interchangeably with each other, even though they are not technically the same thing. The first is something called the equivalence point. The equivalence point is, this is the point where we have exactly reacted all of the reactants with each other. So I started with some number of moles of acid, and I've added an equal number of moles of base to each other. That's what the equivalence point is. Visually speaking, the equivalence point is usually, well, it's darn near impossible to see without some kind of electronic or instrumental kind of help. Because think about it. What color are most acids? Most acid solutions are what color? Yeah, they're colorless. They're optically clear. We can see through them. And they have no color whatsoever. What color are most base solutions? The answer again is colorless. Most of the time, we got colorless solutions out of those. When I put an acid and a base together, most of the time I end up with a colorless and clear solution as a result. There's some other times where we saw the barium hydroxide sulfuric acid example where that one produced a solid and a clear solution. But for the most part, most of these reactions occur and they don't give us any kind of visual cue that something happened. And so from that perspective, equivalence point is really difficult to see from the mind's eye of a chemist. So what do? Well, in short, we cheat a little bit. We introduce something called a chemical indicator. A chemical indicator is a molecule that is pH sensitive, meaning at certain pHs, it's going to have one molecular structure and give us one kind of color. And at other pHs, it's going to have a slightly different molecular structure and give us a different color. And so what we look for is an endpoint, a place in time in our titration where the color change occurs. And when we do titrations, this is ultimately what we are seeking, is the endpoint. Because the endpoint is going to give us a visual cue that tells us, oh, hey, the chemical reaction that we were looking at, it's done now. Now, if you remember to that lab where we combined the barium hydroxide and the sulfuric acid together, we had you do something to that. We didn't just have you dump them together. We had you add an indicator. The indicator in that case was something called phenolphthalein. You saw phenolphthalein in this week's lab as well. Phenolphthalein is colorless in acid solutions, bright pink in base solutions. Somewhere in the middle of that, between that magenta pink and that colorless, is this rosy pink kind of transition that tells us, okay, we've seen a color flip change happen. At that point, that's where our reaction is over. That's our endpoint. Now, why do we use endpoint? Well, it gives us a good estimation of that equivalence point. It gives us a visual cue that is a relatively good indication that we're at or at least near the equivalence point, and we can estimate our concentrations based off of that information. So a little bit more here about indicators. Indicators are often used in titrations. And the reason why is they usually give us a pretty good approximation. Within usually about 1/10 of a milliliter, often less, of what the true equivalence point is. And depending upon our concentration of solution, that 1/10 of a milliliter is not going to make that big of a difference in terms of the overall calculation of the concentration. We might be talking about the difference between measuring 0.890 and 0.891 molar as the concentration. Not too big of a deal. So the indicator on the left here, you know this one well. This is the phenolphthalein. Don't ask me to spell it, even though I just did. Took quite some time to learn how to memorize that one. The indicator on the right here is something called methyl red. This is a different kind of dye. It actually works at a different range of pHs, but the idea is the same in both cases. Phenolphthalein works very, very well for acid-base reactions that have an equivalence point pH right around pH of 8, which most acid-base reactions that we deal with fit in that mold really, really nicely. Methyl red is actually used for pH transitions that occur more toward the acidic side of the pH scale. And so we see, especially with acids that have more than one hydrogen to get rid of, methyl red's a good indicator for those because that first reaction usually leaves behind an acidic pH after we hit that first equivalence point. These are not the only two indicators. There are literally dozens of indicators that all can be used for a variety of different purposes at different times. And the color transitions that they represent are widely varied as well. This is just two of the more common examples. In lab next week, you will get to do this kind of a reaction for yourself. This is what a titration actually looks like. So what you have in the flask here is your acid solution. In this apparatus, which is called a burette, you have your base solution. And so the whole technique of a titration is you slowly add the base to the acid to get to that end point where we see that color transition kind of become permanent for the first time. Titrations are a very rigorous technique. It does take some practice to get used to doing them and doing them right. But once you kind of get the hang of it, you can usually knock them out pretty fast. As far as calculations go, we can use a modified version of that dilution equation. So if you remember from last week, M1 times V1 is equal to M2 times V2. We can use a modified version of that if we include these. These values of N are the coefficients from the balanced chemical equation. So if I have sodium hydroxide reacting with sulfuric acid, the products of that reaction would be water and sodium sulfate. My values of N would be the coefficients attached to the acid and the base. So for the acid, sulfuric acid had a coefficient of 1. My denominator would have a 1. For the sodium hydroxide, my base, it has a coefficient of 2. So I would need a 2 in that spot right there. This is a really useful equation because it allows us to do calculations and determine unknown concentrations with relatively minimal algebraic manipulation. Most of the time, these ratios here are 1 to 1, 1 to 2, 1 to 3 kinds of things. Really, really kind of straightforward and simple. Now we have to use molarity in our M values here. These have to be molarity, but like the dilution equation, we can use any volume unit for V. More often than not, when we're doing our titrations, we're going to be using milliliters because we do titrations with relatively small amounts of these liquids. And so the nice thing about that is since we can keep it in milliliters, we don't have to turn it into liters first to find the number of moles. That's really helpful. Again, it makes the calculations considerably easier, considerably faster. All right, let's look at a couple of examples. We need 28.18 milliliters of a 0.2437 molar hydrochloric acid solution to completely titrate 25 milliliters of a barium hydroxide solution of an unknown concentration. What is the molarity of the barium hydroxide solution? All right. Now, right away, we can look at this and say, okay, I've got a volume and a molarity for the acid, and I've got a volume for the base. So I already got some of those parts of the equation. What I'm missing is the balanced chemical equation to get those N values in the denominator. So before I move on to that, I got to write out my balanced chemical equation. HCl plus barium hydroxide makes barium chloride and water. Now I got to balance it out. I've got 2 chlorines here, so I'm going to need 2 HCl's to balance that. Let's see. I've got 2 oxygens, 4 hydrogens. That's 2 water molecules. So I've got it all balanced out now. And it's a good thing that I did. If I didn't balance it out first, I would have ended up with the wrong value here because this is not a 1-to-1 ratio of acid to base. So I can't just ignore the denominator here. Remember my dilution equation or my titration equation. Molarity of acid times volume of acid over coefficient of acid is equal to molarity of base times volume of base divided by coefficient of base. My molarity of acid is 0.2437 molar. Multiplied by 28.18 milliliters divided by the coefficient 2. And that's equal to my molarity of base, which I do not know what it is, multiplied by 25.00 mils. And the coefficient of the base here is 1. Rearranging, my base concentration is 0.2437 molar times 28.18 milliliters times 1 over 2 times 25.00 milliliters. My base molarity, 0.2437 times 28.18 divided by 2 divided by 25 to 4 significant figures. Divide by 25. So algebraically speaking, I've got MB over here. I've got to divide by the 25 and multiply by the 1 to get the base molarity by itself. Yes, because the 2's still here. This 2 is still there. Okay. 0.1373 molar barium hydroxide. All right. Any other questions from this example? All right, let's try another then. So in this one, we're asked for the concentration of sulfuric acid if 15 milliliters of it reacts with 18.45 milliliters of a 0.0973 molar sodium hydroxide solution. Like with the first one, I need a balanced chemical equation. H2SO4 reacts with NaOH to make water, and sodium sulfate, Na2SO4. To balance that, I'm going to need 2 sodiums, which means I'm going to need 2 sodium hydroxides. I've got 2 hydrogens, 2 hydroxides. That's going to make 2 waters. Same setup as before, just kind of in the opposite direction. This time we're trying to find the concentration of the acid. So the molarity of the acid multiplied by 15 milliliters divided by its coefficient, which is 1, is equal to the molarity of sodium hydroxide, 0.0973 molar, times 18.45 milliliters, divided by its coefficient of 2. Now we need to isolate. To isolate, I'm going to have to multiply by the reciprocal of the fraction that is around MA. So I've got MA times 15.00 milliliters over 1. I'm going to need to multiply that by the reciprocal, 15.00 milliliters over 1. Got to do the same thing to the other side. 1 over 15 milliliters multiplied by 0.0973 molar, 18.45 milliliters over 2. On this side of the equation, the left side, I'm going to cancel my 15 mils and my 1s. All that's left over is the molarity of the acid. On the other side, my milliliter units cancel. Everything else is left behind. 1 times 0.0973 times 18.45 divided by 15 divided by 2. 0.0598 molar sulfuric acid. So this step right here was all about canceling out and isolating that unknown variable. So I had the molarity of the acid times 15 over 1. I multiplied it by 1 over 15 to get rid of that side. Since I did it to the MA side, I had to do it to the MB side as well. That's how I end up with molarity after everything else cancels out. Any questions with this one? All right. I want you to try this one. We've already got the balanced chemical equation set up. We've already got everything kind of there for you. Let's see if you can do something with the data. So we've got 21.33 milliliters of 0.1199 molar sodium hydroxide. reacting with 25 milliliters of HCl, what is the concentration of the HCl? All right, we're running short on time here. I'm just going to flash the answer up. Process is pretty much exactly the same as the previous two examples. Only big difference, the only real difference that we have to look at here, this is the only time where we've had a 1-to-1 ratio. We had exactly as much hydrogen as we did hydroxide. When that's the case, our denominators essentially cancel each other out. This looks exactly like the dilution equation then. And so all we had to do was multiply the molarity and the volume for the base, divide by the volume of the acid, and that gave us 0.1023 molar hydrochloric acid. On Monday, we're going to talk a little bit about one particular property of solutions called osmotic pressure, which is just kind of a general property that we'll discuss, and then we'll get into chapter 13. You should have everything that you need to do the homeworks, though, with what we've done so far. And this, again, should really help you next week with lab, because a big chunk of the lab next week is going to be the titration and doing the calculations with that titration. Have a great weekend. Did you get everything written down?